I want to walk us through how to solve each of these Boyle's law calculations in the problem set. So let's go through the first one together. You decide to climb to the top of two of the tallest mountains. Before you're about to leave on your epic journey, a friend gives you a balloon with a volume of 800.0 centimeters cubed, which is the same as milliliters. It was inflated under standard atmospheric pressure. You climbed two different mountains with this balloon. You climbed Mount Everest, which is 29,028 feet above sea level, and it has an average atmospheric pressure of 221 millimeters of mercury. And you also climbed Mount McKinley, which is 20,320 feet above sea level, and it has an average atmospheric pressure of 345 milliliters of mercury. Before calculating any values, predict which mountain the balloons will have the largest volume. So what I've done in this scenario is I've sort of set up a little bit of a picture to show me what's happening here. So I have Mount McKinley, which is not quite as tall as Mount Everest. At sea level, the volume of the balloon is 800.0 centimeters cubed. And because they've reported the other pressures in millimeters of mercury, I've opted to pick the standard pressure unit at sea level as 760 millimeters of mercury. We know that that is one of our standard pressure units that we can use. I'm going to go to the top of each mountain. We notice that the higher in altitude you go, the lower the atmospheric pressure, hence why Mount Everest has a lower pressure than Mount McKinley. So I would project based on Boyle's law, knowing that volume and pressure are inversely proportional. Because the pressure drops more greatly at the top of Mount Everest, that the volume here will be a lot greater. Then what you do is you use Boyle's law formulas to calculate those values. So what I did was I rearranged P1 V1 equals P2 V2. To solve for V2, I plug in my values, initial pressure, initial volume divided by final pressure, and I get a volume in my calculator of 1,762.3. When I look back at the number of significant digits that are given, here the volume is 4 significant digits, but the pressures are given in 3 significant digits. So the answer on this worksheet is very particular about reporting to proper sig fig. So what I've got here is I have 5 significant digits. Because we can only be accurate to 3, these two are just sort of guesses, so we would report this to be a 0. So approximate volume would be 1,760 for certain. We can't be certain that it's 62.3, let's say. Same thing with Mount Everest. We have a final volume calculation yielding 2,751.1, but we can only be accurate to 2,750 centimeters cubed. So we in fact proved that at lower atmospheric pressures, the volume will be greater. Okay, the next question asks, explain why climbers of such tall mountains need to carry oxygen with them near the top. How does this relate to low pressures described above? So what we've talked about is at higher altitudes, we know that atmospheric pressure is less, and that's due to the fact that there are fewer air particles in the atmosphere at higher altitudes. So as a result, you would need to have oxygen in order to meet the oxygen requirements for your body to actually survive. In number 3, you have a soap bubble and it's blown at a standard pressure, okay? And the standard pressure could be many different units, so we want to read ahead. When a thunderstorm passes later in the day, the pressure becomes 700 millimeters of mercury. So generally when there's storms, pressure drops in the atmosphere. Will the bubble get bigger or smaller? So because we're using millimeters of mercury here, I would pick my standard pressure, which means we're at STP conditions, to be 760 millimeters of mercury. If I have a drop in pressure, I can expect the volume to go up. Let's see if that's the case. When I plug in, rearrange, I in fact get 54.3 milliliters. I want to make sure that I pick milliliters because that was the original unit for the volume used. Notice that my millimeters of mercury cancel out, so the volume did go up. Okay, in question number 4, you have a balloon. It's inflated to a volume of 5.0 liters at a pressure of 0.9 atmosphere. It rises to an altitude where its volume becomes 25 liters. Will the pressure around the balloon increase or decrease? What will be the new pressure? So let's take a look at what is given. We're given the initial volume and the initial pressure. The final volume of the balloon goes up to 25. So we know that if volume goes up, then the pressure must go down. So we can expect our final pressure reading to be less than 0.9. Let's take a look when we rearrange the formula. P1V1 equals P2V2. When we rearrange to solve for P2, V2 goes to the other side of the equal sign, opposite operation, so it's being multiplied here. It will be divided on the other side, and we end up with a value of 0.18 atm, atmosphere. We can only report 2 significant digits. This volume is 2 sig fig. This atmospheric value here is 2 significant digits. Remember, the 0 that's out front is a placeholder. It's not significant. This volume reading is 3. We can only report to the fewest number of sig fig based on the values given in the question. 0.18. Remember, that is just a placeholder, ATM. Let's take a look at number 5. Okay, so number 5, we have a scuba diver. And a scuba diver inflates a balloon to 10 liters at the surface. And he takes a dive at a depth of 100 feet. The pressure is a lot greater. It's 4 atm. So what ends up happening to the volume of the balloon? So we know that at the surface, we're at STP conditions. So because they reported this pressure in atm, I'm going to pick my initial pressure to be 1 atm. I solve for the new volume. I see that pressure went up, so the volume of the balloon should go down. So let's take a look. Rearranging, solving for V2. 1 atmosphere times 10 liters divided by 4 atmospheres gives you 2.5 liters. So the volume, in fact, did go down. I do need to answer the question. So the volume of the balloon decreased since the pressure increased. Let's take a look at question number 6. The living quarters of a space shuttle has a volume of 20,000 liters, which they've also put into scientific notation, 2.00 times 10 to the 4 liters. That means the same thing. Putting it this way, we see that that is 3 significant digits. Any zeros after a decimal are significant. And they're saying that the living quarters is at a pressure of 12.0 pounds per square inch. If all the air were lost, it would have to be replaced from a compressed air cylinder, which has a volume of 50.0 liters. What is the pressure in that tank? In other words, how much pressure would it take to compress all the air in the shuttle into a 50-liter space? So I rearrange. I am solving for P2. And we end up with 4,800 pounds per square inch. That is PSI. Okay, means the same thing there. This next one, we are back to the space shuttle, and we have living quarters, and we have a volume of 20,000 liters where you are living, and you are at a pressure of 500 milliliters of mercury. So let's just take a look. I have a little drawing here. So you are an astronaut, I'm assuming, since you are living in space, and you are living in this little space shuttle here. You are going to then dock with a bigger space lab that has a volume of 20,000 liters of space, okay? So it has no air in it. The minute you open up the hatch, the air is now free to move between both compartments. So what is the air pressure become when the hatch is now opened? So originally, your original volume is 20,000 liters at 500 milliliters of mercury. You open the hatch, and what you do need to realize is that the second volume is both volumes of the rooms added together. So you are at a total volume of 250,000 liters for your V2. What is the final pressure? When I rearrange, substitute in, I get 40 millimeters of mercury, and that would be 40.0 since I am reporting to 3 significant digits. because both of my volumes are 3 sig fig, whereas the pressure was 4 significant digits, we can only report to 3. The last question, okay, is one where we have a fountain pen, and it has a total volume of 2.5 centimeters cubed. So the total volume of the pen. It is half filled with ink, and that means that the other half is gas, okay, or air. So remember that gas laws only apply to gases. They don't apply to liquids. So when we're talking about Boyle's law formulas, we have to look at what is the volume of just the air in the pen or the gas in the pen. So because the entire pen itself is 2.4 centimeters cubed, half of it is 1.2 centimeters cubed of air. So we have this pen. You are at a pressure of 780 millimeters of mercury. You put it, the pilot puts it in his pocket, and he flies to an altitude where the pressure drops. How much ink will leak out of that pen? So what I do is I'm solving for V2. Now, what V2 tells me is, well, this air inside the pen, we know that it is going to occupy a greater amount of space, because as you go up in altitude, volume of air or gas increases, okay, because the pressure decreased. So that means now the air is going to occupy not 1.2 centimeters cubed, but it occupies 1.8 centimeters of cubed. So that means that a portion of the ink then will get squeezed out of the pen. How do I figure that out? Well, I know that if I expanded to 1.8 and it originally had 1.2, I subtract the 2 and you get 0.6 centimeters cubed. Or you could think of it another way. If you look at the total volume of the pen and how much gas occupies the pen now, you can subtract and you'll get 0.6 centimeters cubed. So those are some explanations for the entire Boyle's law problem set.